Welcome back. Today we're going to be talking about Baldwin's rules and the probabilities of ring closure. So to introduce Baldwin's rules, these were developed to explain trends that involved ring closure, wherein some reactions were found to be favoured while others were not, even though on paper both would seem to be plausible outcomes. Typically the reason for this comes down to reaction kinetics rather than certain pathways being allowed or forbidden. So basically, one reaction pathway is considerably faster than the other one, such that at the end of the reaction, you don't see the slower product. Part of this comes down to orbital overlap, or stereoelectronic factors, which favours certain combinations of ring sizes and reaction pathways. Baldwin's rules aren't absolute. There are several exceptions whereby you can actually get the forbidden product at the end. However, a lot of these centre around either hypervalent atoms, so examples like sulfur and phosphorus, or catalysis involving transition metals. So first we should talk about the nomenclature of assigning a reaction by Baldwin's rules. So the first aspect is exo versus endo, and we assign this based on the bond that breaks being either outside or inside the ring that forms. Now, when we say bond breaking, what we mean is a drop in the bond order. So something like a triple bond becoming a double bond counts as a bond breaking. Same with a double bond becoming a single bond or a single bond breaking proper. So if we have a look at the examples, if we look at the bond that's going to break, we have a double bond shown in red, and it is reducing in bond order to a single bond. So we count that as a broken bond there. If we look at the 5-membered ring that's forming, that double bond is situated outside of that 5-membered ring. So we would class this as an exo reaction. Over here we have an example of an endo reaction. It's basically exactly the same thing. However, this time when the double bond breaks, it's situated within the 6-membered ring, which is the product. So, because this broken bond, shown in red, is forming part of the ring, we class this as an endo reaction. The next part of the classification involves looking at the atom which is subject to the nucleophilic attack. There are 3 options, which are shortened to dig, trig, and tet. And effectively, I've highlighted that atom in blue in each of these 3 examples. So looking at the first one, this carbon is subject to nucleophilic attack, and it's tetragonal, meaning it has 4 functional groups attached to that carbon. Because of that, it gets the classification of tet. Looking over here at this carbon now, it's trigonal, meaning it has 3 functional groups attached to that carbon, a hydrogen, this Y group, and this carbon. So this gets shortened to trig. And the final example, this carbon is digonal, or digonal, which means there's only 2 chemical groups attached to it. Thinking very quickly about the previous slide, if we look at the bond that's actually breaking across all 3 examples, we see that it's situated outside of the ring being formed. So all of these are exo reactions, giving us our exotet, our exotrig, and our exodig. Now, the final part of the classification is you need to quantify the number of atoms within the ring being formed. So if we take a look at our first example, it's a 5-exo-dig reaction by Baldwin's rules. And if we take a look at the ring being formed, we see that there is a 5-membered ring formed in this reaction. The bond that breaks, which is highlighted in red, is situated outside of the ring, therefore it's an exo reaction. And if we look at the carbon atom that's being attacked in this reaction, it is a digonal carbon. So altogether that gives us this reaction as being a 5-exo-dig reaction. Looking at the second example, this time we're forming a 7-membered ring at the conclusion of the reaction. If we take a look at the bond that's going to break, it's situated here in red, and it actually forms part of the ring in the product. So that gives us a 7-endo. And then lastly, if we take a look at the carbon, we can see that it's a trigonal carbon because it has 3 groups attached to it. So the classification by Baldwin's rules is a 7-endo-trig. So with the nomenclature out the way, we can start looking at the reactivities as predicted by Baldwin's rules. And one thing we'll touch upon first is SN2 reactions. This should be basic revision, but if we have a look at the HOMO, highest occupied molecular orbital, we can see we've got this nucleophile and we have this lone pair approaching the reactant. Over here, looking at the LUMO, we can see we've got this anti-sigma bond arrangement, and this lobe of the anti-sigma bond is going to be stabilized by the nucleophile as it approaches. Now, because the anti-sigma bond is going to be stabilized, effectively it's going to nullify this bonding force between the carbon and the bromine. That gives us this transition state over here, and ultimately the bromine will be released, having taken the electrons from the bond, and we get this inversion of stereochemistry. So basically it's a backside attack reaction. Now, the question, if this was Baldwin's rules and we were forming some kind of a ring, is do you require this 180-degree approach of the nucleophile, or can the reaction sustain differences in angle of the approach of the nucleophile? This idea kind of underpins whether or not a cyclization is going to be favoured according to the rules. So just to kind of give you an example of what I'm talking about, here we have another example where we might consider, can an SN2 reaction occur via a backside attack? And we can see in this instance, for an intramolecular reaction, this can't actually sustain a 180-degree approach from the nucleophile. It's effectively locked in this conformation like so. So can this transition state form, giving us this product? And the answer is no. You do not see any intramolecular reaction giving you this product by the way that it is drawn. You can form this product from this starting material, but it all occurs by intermolecular reaction. So effectively you need multiple molecules reacting with one another for this reaction to be seen. We can even expand this concept. So can we redesign our starting material to affect something that gives an angle closer to 180 degrees? And once we get to this 10-membered ring, so this vastly expanded intermediate transition state, we're still not at 180 degrees for the approach from the nucleophile on the functional group, but once we get to this 10-membered ring, you actually start to see intramolecular reaction occurring. But even now, it's not particularly favoured. So you only see 16% intramolecular reaction, with the vast majority, 84%, being intermolecular reaction, where multiple molecules come together rather than the molecule keeping it in-house and only using its own functional groups. And so this idea of atom approach trajectories underpins a lot of Baldwin's rules. Essentially, the assumption is that there is a strict requirement on the transition state and that atoms need to make a proper approach for the reaction to occur. These are the postulated approaches that need to be satisfied in order for the reaction to be kinetically favoured. So if we take a look, the top one is basically our SN2 scenario. Our approaching atom needs to have a 180-degree angle to the leaving group, shown over here. If we're looking at a trigonal system, the approach becomes 109 degrees relative to the leaving group, or where the bond is going to break. And finally, for a digonal system, that angle becomes 120 for two functional groups to give us this product shown over here. Now, this bottom example has a bit of an asterisk around it. The reason for that is if you look at the experimental evidence, it doesn't really support this idea as well as the top two scenarios do. So now we've got that out of the way, let's look at some of the predictions made by Baldwin's rules. For n, so essentially, any number of exotet cyclizations, all are allowed provided that there are enough atoms to actually form a ring. So effectively, you need to start at n being 3, but as you increase that number, any exotet cyclizations should be favoured. You do need to consider sterics as well as the likelihood of the transition state forming, but there are even examples of these 3-membered strained systems forming according to Baldwin's rules. Now let's consider some of the stereoelectronic effects that are going to influence whether or not bonds can cleave or form. One of these relates to an earlier episode on the anomeric effect, and that is when forming a 3-membered cyclic system. So here we're talking about epoxides. If we have the nucleophile in an antiplanar arrangement to the leaving group, which is Y here, it's going to be favoured. And we can take a look at the intermediate in the reaction, and the reason for that is while in this antiplanar orientation, the reaction can occur while the ring is in this chair conformation, and that conformation is favoured for six-membered ring systems. So we can see the transition shown here. If we think of this as the anti-sigma bond, so we need to break this bond in order to release the Y group, the nucleophile, or the oxygen, is relatively well positioned to sit underneath this anti-sigma bond, stabilising it in order to form this epoxide species here. If we instead consider this equatorial positioning, so instead of having our leaving group and our nucleophile here in the axial positions, we're putting them both in the equatorial positions instead, reaction cannot actually occur while in this favoured chair conformation here. What you need to see is a change in conformation to this twisted boat form of the six-membered ring, and that then brings these functional groups into alignment. So the nucleophile and the leaving group, they're aligned together, it can occur, but this reaction is very slow. The reason being that the chair conformation, keeping the functional groups apart, is much more likely than this twisted boat conformation that allows them to align and react. This just gives you a quick reminder on the conformations of six-membered rings. We've got this chair conformation on either side. If we are going to get to this twisted boat conformation up here, firstly we can see it's higher in energy and thus less favoured, and we also have to get over this energy barrier in order to reach it. So if we think about the propensity for six-membered rings to be in each of these forms, 99% of the time it's probably going to be sitting down in this chair conformation. Occasionally, 1% of the time, it'll get over this energy hump and it'll be in this twisted boat conformation that allows the reaction to occur. Like I said earlier, Baldwin's rules doesn't state what's forbidden and what's allowed. It's more about rates. So what occurs quickly and therefore you see it versus what is really, really slow to occur and therefore you don't see it. So chair conformation is fast, twisted boat conformation is slow. Therefore, you typically see this reaction occurring while this reaction does not occur, at least not as quickly. So what we just discussed covers the formation of epoxides, but the first Plattner rule, this covers the opening of epoxides, and it's basically the same concept again. If you have this diaxial orientation of nucleophile and leaving group, this is going to give you the best overlap of the anti-bonding Cy or the C leaving group orbital with the non-bonding electron pairs of the nucleophile. So if you want to open up an epoxide, what you need is your nucleophile to approach, which gives you the diaxial orientation in relation to the atoms of that epoxide. Much like before, you could see other orientations occurring, however it's going to be a lot slower and so disfavoured unless there are no other options available. So here we have our two epoxides here. One thing to consider is how these epoxides are forming. So essentially we've got this double bond, which we are then reacting to give us this epoxide form. That's kind of interesting from the perspective of the various conformations that we see in a six-membered ring. So going back and having a quick look, considering we now have a double bond in this position, essentially it's locked in a half-chair conformation because we're going to have a linear bond to our double bond and then a linear bond leaving for that one. So because we have an alkene or a double bond in our six-membered ring, we're effectively locking it in this half-chair conformation, which means that adopting this twisted boat conformation becomes a lot easier when we're starting from either a double bond or we can imagine an epoxide attached as well. It's going to have the same sort of locked linear conformation across here. So for that reason, we draw our nice linear bond like so because our six-membered ring is locked in this conformation by either the double bond or the epoxide. It doesn't really make a difference. It's this straight conformation across here. So now we can consider where is the nucleophile going to actually attack. Is it going to attack on this side of the epoxide or this side of the epoxide? Now, the way I do this is when the nucleophile comes up and attacks a specific carbon, I drop that carbon down to meet the nucleophile. So if we have a look at this diagram over here, nucleophile is approaching on this side to this carbon, so we can drop this carbon down and then redraw out our six-membered ring like so. If we take a look at this conformation, this is effectively our twisted boat conformation shown here. So it's relatively high in energy. It's lower in energy than our linear arrangement, so it is favoured to form this. But if we compare it to the nucleophile attacking the carbon on the other side, if we drop this carbon down and give this diagram here, we can see that our six-membered ring is now in the chair conformation. And this is going to be the most favoured conformation in a six-membered ring. Let's have a look. So in terms of energy, chair is down here versus twisted boat, which is up here. So the nucleophile attacking on this side is going to be favoured for the reason that the six-membered ring that results at the end is lower in energy. So comparing these two reactions, even though on paper it doesn't really look like either carbon should be favoured, the bottom scenario is favoured because instead of getting this twisted boat conformation, which is higher in energy after the reaction, you instead get this chair conformation shown here, which is lower in energy. And indeed, there's some really interesting real-world uses for this information. One of those is the chiral resolution of limonene oxide. So here we have our six-membered ring. It's got an epoxide embedded in that ring, so we can draw it out like so with our linear arrangement. We have two chiral species. We're reacting each with a nucleophile. Let's say it's an identical nucleophile. You would initially think there's no real difference beyond the chirality of these two molecules. They should react identically. But in fact, one is more reactive than the other. And if we take a look, it's the top example for the reason that we talked about before. If this nucleophile is attacking from this direction, what we get is our nice chair conformation shown here. So this is low in energy, whereas in this situation with the nucleophile attacking from the bottom, this gives us our twisted boat conformation, which is higher in energy. So effectively, if you play around with the conditions, you can actually affect only one of these chiral species reacting, leaving the other unreacted. And once you've done that, you have two unique chemical species. You would be able to separate them using chromatography or something like that. So effectively, you can isolate one chiral enantiomer away from the other one. Now, moving on to N-endo-tet cyclizations. These are going to require a 180-degree angle between the nucleophile and the atoms whereby the bond is going to break. We covered this earlier in the example. You basically need a ring size of at least 9 or 10 for any intramolecular reaction to occur. So typically these instead occur intermolecularly. Again, you can be clever and actually harness this information. So here we have an oxygen atom transfer reaction. We're going to set up the reaction so that an intramolecular reaction is preferenced. And one thing we know from the previous slide is you need a cyclic intermediate that has at least 9 or 10 atoms in order for this intramolecular transfer to occur. So here we have a big long unsaturated alkyl chain. I'm not going to draw out the intermediates, but we can sort of visualize in our head the cyclic intermediate that would need to form in order to get our nucleophilic oxygen to approach the double bonds shown here. And the reactivity is only going to get stronger the further down the chain you get, because you're increasing the number of atoms in that cyclic intermediate. So I don't know how large the intermediate would be to put the oxygen atom down and form the epoxide down here, but this double bond is going to be considerably faster to react than any of the other double bonds, which would form smaller cyclic intermediates. So this gives us our selective epoxidation only of the furthest double bond down the chain. So thinking about these tetrahedral reactions by Baldwin's rules, there are going to be exceptions. So as soon as you start including a hypervalent element, so something like silicon, phosphorus, where we can expand out beyond the octet rule, all bets are off. So here we have another example of an exception. So we have a reaction between two species. One of them contains a methyl group, the other contains a trimethyl silyl group. Now, this one has silicon in it, which means we have potentially a hypervalent element in our reaction. We can break the octet rule briefly in this reaction. And indeed, if we take a look at our intermediate, that is what occurs. We can get this transfer of the silyl agent across onto the oxygen as the reaction proceeds, giving us this product here. Similar things cannot occur for the bottom reaction. We can't get that breaking of the octet rule with carbon. We can potentially see it with silicon though. N-exotrig cyclizations. All of these are allowed provided you have enough atoms to form a ring. So the N has got to be 3 or bigger. Very similar to the N-exotet that we discussed earlier. It's not worth rehashing beyond that. I've just shown a simple example down here, giving us our strained 3-membered ring product. N-endotrig cyclizations where N is 3 to 5. These are disallowed, although there are similar relaxation to the rules if you've got some sort of hypervalent element available, like, say, sulfur here for our nucleophile. Top example can proceed, bottom example is forbidden. Now let's consider a 5-endotrig versus a 5-exotrig reaction. And we're going to do that looking at this central molecule shown here. There are 2 possible ways that this reaction could proceed. So we have the 5-endotrig approach, whereby our nucleophilic amine attacks our double bond here, forming our central cycle here. The alternate is we don't get attack on this double bond, and instead it attacks this methyl ester group, shown with the green dashed arrow. So if 5-endotrig was to occur, we would get this product over here. If 5-exotrig were to occur, we would get this product over here. And indeed, this is a really good example of Baldwin's rules in action. Because 5-endotrig is disallowed, we don't see any of this product over here, whereas the 5-exotrig is allowed, and we only see 100% of this product over here instead. So why should 5-endotrig be disallowed like this? If we visualize the orbital interplay that would have to occur to get it to work, we can see that just none of the approaches are suitable to facilitate this reaction. Thinking about our double bond, if we're going to break that double bond, we need an anti-pi bond, which was shown here with the 2 p orbitals misaligned. Now, if we consider the approach of the lone pair towards this anti-pi orbital, if it's approaching in the plane, meaning we just imagine a flat 5-membered ring, these orbitals are going to approach sort of towards the center of this p orbital. It's not going to approach in a way that either favors either side or either lobe of this p orbital. It's essentially coming in towards the middle, favoring neither side. So this is not a good way to stabilize the anti-pi orbitals. Alternately, we can think about an out-of-plane approach whereby we bend out these carbons, placing our nucleophilic lone pair kind of above the anti-pi orbitals, but the angle of approach isn't suitable to facilitate the reaction. So neither of these are particularly good for stabilizing the antibonding orbitals. And for that reason, this 5-endotrig pathway just isn't favored. No such problems though when attacking the methyl ester. Next thing we'll consider is a 5-exotet versus a 6-exotet cyclization. So we're going to look at an enolate alkylation shown below. Here, both sterics and stereoelectronics are going to influence the outcome of the reaction. Taking a look at our 2 nucleophiles, in the top example, we've got an enolate nucleophile, whereas in the bottom, we've got more of a ketonate nucleophile. So we can think of keto-enol tautomerism between these 2 forms. For the top example, the oxygen acts as the nucleophile, so this is the 5-exotet. 100% this product form, 0% this alternate product forming. Whereas in the bottom example, we've got a nucleophilic carbon acting as our nucleophile, almost 100% of this 6-exotet reaction seen. So why would that be? Well, interestingly, it comes down to the orientation of the lone pairs in our nucleophiles. So if we think about our 5-exotet example, and we think about the orientation of the lone pair coming off that oxygen, drawing out our intermediate, we can see that we can orient that lone pair relatively well to stabilise the anti-sigma bond that needs to break in order to release this bromine atom here, giving our product. Given it's an oxygen with a negative charge, it's going to have 3 lone pairs, and the orientation of those lone pairs is going to be effectively tetrahedral. So that's quite an expanded range of angles whereby that nucleophile can attack, and that allows this 5-membered transition state. If we consider instead the carbon nucleophile, the lone pair on that carbon is going to be in a p orbital. You can consider this p orbital as being conjugated with the adjacent p orbitals in the ketone. So this lone pair in this p orbital is lined up with the adjacent p orbitals next door to it. So it doesn't have the same kind of flexibility as the lone pair on the oxygen does in the other example. So what we really need is this 6-membered intermediate. Only with the extra carbon in the chain can this anti-bonding sigma arrangement be in the proper orientation to be stabilised by this carbon nucleophile here. Now on to digonal carbon. Both the 3 and the 4 exo-dig cyclizations are disfavoured, whereas 5 to 7 exo-dig are favoured, while 3 to 7 endo-dig are also favoured. And these are largely allowed because our triple bond gives us pi orbitals that are almost always correctly aligned towards our nucleophile, as shown here. Now, the angle of attack argument posited by Baldwin, there was a reason why he put an asterisk on that. There has since been experimental evidence, both using computational chemistry as well as X-ray crystallography, that's shown that this 120-degree angle of approach of the nucleophile and of the leaving group leaving is not actually what you see experimentally. So here's a good example of a 5-exo-dig reaction that you can find in the literature. We have our starting material and we apply a base, which deprotonates adjacent to our ketone group. From the previous example, we know we would have our p orbital here, which aligns the lone pair up towards this anti-bonding pi orbital directly above it. So the alignment between our nucleophile and our anti-bonding p orbitals is good enough to stabilize this anti-bonding configuration, and so our triple bond breaks to give us our double bond in the product here. So to summarize, we've covered the tetrahedral carbon examples, those being N-exotet and endotet cyclizations. Some exceptions include the later period elements, so things that can partake in hyperconjugation, like silicon, like phosphorus, like sulfur, or any form of transition metal catalysis will get you around Baldwin's rules to access forbidden products. Here is just the quick summary of Baldwin's rules, showing the ones that are favoured with a tick, while the ones that are disfavoured are highlighted with a red cross. That's the quick overview of Baldwin's rules. Thanks for watching.